Welcome to everyone who's joined us for this opening session of the International Science School Online for 2021. Before we begin our meeting, I'd like to acknowledge the traditional owners of Australia and recognise the continuing connection to land, water and culture. I'm currently on the land. When I say I'm actually speaking to you from the United Kingdom right now, but our program is coming to you from the land of the Gadigal people of the Eora Nation, and I'd like to pay my respects to their elders, past, present, and emerging. I further acknowledge the traditional owners of the country on which you are on, and pay respect to their elders, past, present, and future. So on that note, I would like to officially get things underway. We've been unofficially getting things underway for far too long. I'd now like to officially get things underway. The International Science School has a very long history. We've been going since 1962 as a student program, and even several years before that, back into the late 50s, when the ISS kicked off as a program for teachers in New South Wales. So it's a very, very long and prestigious history of the program. And you, all of you joining us for the first online ISS, you're contributing to that. We are carrying out a bit of an experiment over the coming week. We've never done a fully online program before, and I'm really excited to see how this one turns out. There's a lot of really positive things about doing things online. For one, I haven't been running around like a crazy person after all of you, trying to get you out of bed and off to the first lecture on the buses since about 6 o'clock this morning. No, it's far easier to get you actually into a program when it's online. Listen, before we get into the first lecture, there's someone that I would like you to meet. This is a person who is here to represent one of the really important parts of this program. That person is himself a geophysicist by trade. He did a degree in geophysics at the University of Sydney a number of years ago. And he's currently responsible for a whole range of different minerals and mining portfolios and programs across the country. He's director for one of the world's largest mineral sands projects and portfolios, managing a global team. He's got several years of experience across exploration, resource development, and project management, across a wide variety of different commodities and resources. But most importantly for us, he is the president of the Physics Foundation. And the Physics Foundation is a group set up by our original patron and founder, Professor Harry Messel. This is the Professor Harry Messel International Science School. The foundation was set up as a way of funding research, education, and science outreach based within the School of Physics at the University of Sydney. So our first guest this morning, who would like to give a formal welcome to everyone here today, is the president of the Physics Foundation. I would like you to make very, very welcome Michael Winternuts. Now, when I say make very, very welcome, normally if we are in a hall, I'd ask you to all bang your hands together in the traditional fashion. Well, you can't hear each other, but I'd like you to do it anyway. I'd like you at home, where you are watching this, just give him a rousing round of applause. Please make very, very welcome Michael Winternuts, the president of the Physics Foundation.
Thank you, Chris, and good morning all. Special guests, Honorary and Life Governors of the Physics Foundation, Deputy President James Kirby, Head of School Professor Celine Bone, and most importantly, ISS scholars, welcome to this ISS 2021. It is a great pleasure and honour to be here this morning, beaming out to the most talented group of science students in Australia. The ISS has a proud history of promoting excellence in science and education in Australia and indeed globally. Indeed, many ISS alumni have gone on to become global leaders in their fields. Of course, there are our usual overseas ISS partner countries that are absent this year. So on behalf of the Physics Foundation, ISS alumni, and indeed the current ISS cohort, we send our apologies and well wishes to our partner countries for what is a challenging time across the globe. And we certainly look forward to welcoming our overseas partners back at the next ISS. Scholars, this is the most exciting and challenging time to be studying science. So many boundaries are being pushed, so many norms questioned, and with this lies an immense world of opportunity for you to embark into. The purpose of the ISS is to make you realise that you're important and treasured. You're no different to the Roger Federers of the tennis world. Just as we've seen Roger shape tennis history over the last 2 decades, you too have the opportunity to make a difference, to shape history. You too deserve to be rewarded and recognised. And this is the purpose of the ISS. This week, you will have the opportunity to hear from some of the world's leading scientists and top minds from secondary schools across the country. I encourage you to challenge each other, ask those curly questions, throw that idea across the screen. It is these opportunities that often create a spark in the world's most brilliant minds. Within the School of Physics here at the University of Sydney, for example, is a world-renowned Nano Institute led by Professor Ben Eggleton, where Ben and his team are looking to use cutting-edge science, outside of the box thinking, to develop a photonic chip. Indeed, what we learn from this is that physics has implications for everyday life across a diverse array of fields, from environmental science to biology to medicine to preventing modern slavery. Many ISS alumni have proceeded to become movers and shakers in their respective fields. I'm sure that we will see your names continue to emerge over the decades to become, just as so many other ISS alumni have. If I can finally leave with you 2 words of advice. Firstly, I encourage you to focus on your passion. If you're going to be a geologist, be the best geologist you can be. If you're going to be an astrophysicist, be the very best astrophysicist. If you're going to be a mathematician, be the best. And secondly, and indeed as my grandfather often told me, remember, the harder you work, the luckier you get. Please enjoy your week. We look forward to seeing you online. Thank you.
Thank you very much, Michael. And of course, behind Michael, as he was sitting there talking to you this morning, was a picture of a whole bunch of different pictures of Harry Messel himself, because Michael Wintonitz is, of course, Harry Messel's grandson and used to sit for many ISSs in a row in that front row of the lecture theatre for the International Science School, watching all the lectures next to Harry himself. And I'm going to be talking a little bit more about Harry to tell you a little bit about his legacy as the week goes on, because it's important you know how we got to where we are. And it is a very sad thing that you, the students in 2021, don't get to experience what it's like to have an ISS with Harry actually there, because Harry would sit in the front row of the lectures and he wouldn't think twice about maybe halfway through one of the lectures getting up and speaking his mind. If there was something that he thought the students really needed to know about, he would interrupt the lecture and just tell everyone exactly what he thought. Or he would ask a curly question of the lecturer right in the middle of the lecture and really put them on the point. He didn't mind, because it's all about the intellectual pursuit and it's all about pursuing those really interesting ideas. So it's a shame we don't have Harry with us, but what we do have is this amazing legacy, which is brought to us through the efforts of the Physics Foundation. So thank you so much, Michael, and thank you so much to everyone who's contributed towards the program as it is today. Right, so on to the next part of the show. I'd like to introduce our first speaker for the week. Our speaker actually completed her Bachelor of Engineering back in 2000 and got her PhD in 2005 from the University of New South Wales. And in fact, just a couple of years ago in 2015, she was one of the speakers at ISS 2015 when she was one of the senior researchers in her group at the University of New South Wales. We liked her so much that we actually decided to grab her and make her one of our own at the University of Sydney. So she is now the John Hooke Chair of Nanoscience here at the University of Sydney, based in the School of Physics. Her research interests include engineering of solar materials, and in fact, she's not just interested in this stuff, she's actually doing it better than pretty much anyone in the world. Some of her solar cells have set energy efficiency world records, and she works in the area of highly durable perovskite, I need to get that word right, solar cells, which is placing her research at the forefront internationally in this research area. Would you once again please bang your hands together very, very loudly so that we can hear them across the entire country for Professor Anita Ho-Baillie.
Thanks very much, Chris. Thanks for inviting me back. Okay, so today I'm going to talk about the status of photovoltaics and the role of R&D and what we're working on in terms of the next generation solar cells. So why renewable and why solar? Well, that's because of climate change. We have spent all of our quota for carbon dioxide emission. We're actually heading towards a world that is 1.5 degrees warmer than the world we had before the Industrial Revolution. So if we have 1 to 3 degrees global warming, we're actually going to lose most of our coral reefs and Arctic summer ice and most glaciers. And if we're heading towards 3 to 5 degrees Celsius of global warming, 1 in 6 species will go extinct. We'll lose our rainforests and carbon sink, and we will have land submerged, which is occupied by 500 to 700 million people. Now in 2011, there's this guy called Professor Hans Hooke. He came to Australia and he was the climate change advisor to German government. And an Australian journalist asked him, what is the difference between 2 degrees and 4 degrees of warming? And his answer is the difference is human civilization. In fact, if we're heading towards 4 degrees warming, only 10% of us will survive and probably will be living in Tasmania. Now we can see, we can feel, we can, we hear about the effect of climate change on the world. We also hear a bit of political noise as well, isn't it? But despite all that, we're actually doing quite well. So the left graph shows that since 2013, we have really reduced our reliance on fossil fuels. We've been adding more renewable energy each year than coal, natural gas, and oil combined. And the right graph shows that since year 2017, we've been adding more solar photovoltaic solar cells each year than wind, hydro, and other renewable energy sources combined. Now, there's also been a steady increase in the deployment of renewables. Now it makes up 27.3% of total energy production in 2019, up from 24.5% in 2016. And you can see that photovoltaics has increased dramatically from 1.5% in 2016 to 2.8% in 2019. In fact, in 2020, 30%, almost 30% of our energy production comes from renewables. So I'm going to throw a quiz at you, as it's not hard. Which one of the following is true? So there's a multiple choice, and you can put your thumbs up for answer A, B, or C. So in terms of the share of renewable energy, it's part of the total in 2020. A, the UK is leading the world at 42%, followed by 29% average, and Australia at 28%, followed by US at 20%. Thumbs up if you think this is true. So I've got 2, I think. Now B is saying Australia is leading the world with 42% of total energy production come from renewables, followed by the world average, and then US and UK last. God, wow, it's increasing. I can see it's going up and up and up and up and up. So B seems to be a popular answer. 26. Right, C. US is leading the world, having 42% renewable, followed by a world average at 29%, and then Australia and then UK. Right. Going up as well. Well, I'll just tell you the answer. The answer, surprisingly, is actually A. UK has a lot of wind energy, believe it or not. I'm quite surprised too. Anyway, well, what does it mean to you? What does it mean to you apart from a cleaner world? Well, that's where all the money and jobs are going into for renewable energy. Now, solar is actually very interesting. So even though it only makes up 10% of the total renewables, it actually takes up 1/3 of the renewable energy jobs. And you can see how it coincides with the amount of investment as well. Now, why is it the case? Why is PV deployment so widespread in the world? It's because the cost of solar photovoltaics has dropped dramatically in the last 10 years, by 10 times. So in 2011, it cost $4 per watt to make a solar module. And now it only costs 40 cents per watt to make a solar module. So it's interesting that I was interviewed by ABC about this article by International Energy Agency, pointing out that the cost of solar is now cheaper than coal or gas. And I got dragged into commenting about government policy on gas-led recovery, but anyway, I dodged the question. So you can see on the top left graph that the cost of solar has gone down so much so that it's actually beneath the cost of fossil fuel. I hope you can see the screen. Now, Chris, you may remember Professor Martin Green in 2011 actually gave a talk in ISS. And Martin Green is the director of Photovoltaic Research Center at UNSW, whom I worked closely with when I was at the center. Anyway, he showed a graph that is produced by Professor Emmanuel Sachs at MIT. And he plotted this learning curve of solar based on the production of solar. So basically what he's saying is the cost of solar as the cumulative production of photovoltaics doubles, and the rate of cost reduction is by 24%. Now, what the learning curve was predicting in 2011 is saying solar in 2020 will be 5 cents per kilowatt hour. And what have we got in 2021? There it is, 5 cents per kilowatt hour. It also predicted that solar will make up 7% of total energy generation. And here we're at now. So it is absolutely amazing how things can get cheaper as we learn by doing and with economies of scale. So how are we doing in Australia? We're doing quite well. 10% of our energy production comes from solar, and we contributed 3% to total PV additions last year. And I want to stress that PV is also doing really a lot of good to developing nations. Globally, we still have around 10% of the population, which is around 800 million people, have no access to electricity. And it was worse 3 years ago. It was 1 billion people, around 14% of the population. So why the drop? And that is solely because of the deployment of distributed renewable energy systems, mainly solar home systems. So many of these countries, they receive 0% interest loan from the World Bank or donors or government. And instead of using the money to pay for diesel fuel, they use the money to pay down the debt for solar, and only for 2 years. And after that, they're loan free and they have access to free electricity. Now, these are the photos that we took. So this lady there with the red cap is actually myself. So we took a bunch of students, 12 of undergraduate students, and went to Nepal. And we installed a simple solar battery system. And all we did was provide lighting to the medical clinic. And the medical clinic is in a remote village in Nepal, but served 30,000 people in the region. Now, before we came, there was no running water. And after we installed the system, it was just amazing to see something so simple and basic to us would make such a difference to them. And after that trip, another group of students went back and they installed another solar system, powering the fridge to store the medicine that is needed in that region. Okay, so let's go. Yeah, let's look at how solar cells work. Well, you need a semiconductor and light. Because solar cells are made of semiconductors. Semiconductors are somewhere between conductor and insulator. Well, the difference between a conductor and insulator is how tightly the electrons are held. So for example, on the left, you can see a sodium atom, and it's got one electron on its outermost valence shell. And you can see the electron is not tightly held, and therefore it can move freely. And therefore sodium is a metal. And you can see because of that, the valence shell is also the conduction shell. On the right-hand side, we've got chloride there, chlorine, which on the other hand's got an outer shell full of electrons, and they're tightly held, and therefore chlorine is it's an insulator. And for it to become for the electron to become conductive, actually needs to move from the valence shell to the conduction shell. Now, a semiconductor is a material where the forbidden gap here is actually narrow enough that the electron can jump from the valence level to conduction level if it's given an enough amount of energy. Now, in a solid, atoms are held tightly together, and they don't all take up the same energy levels dictated by quantum mechanics. So instead of having one energy level, they actually have energy levels that are close together, and they can be considered a band, or we call it an energy band. So in a semiconductor, when there is enough energy, for example, heat, electron will actually jump from the valence band to a conduction band, and an electron is able to move freely. Now, there is a hole left behind by the electron, which is positively charged, and is also allowed to move freely. Therefore, it is possible to consider hole as a quasi-particle that also contributes to the electronic property of a semiconductor. Okay, so we just stepped you through semiconductor. How about light? Light, well, in the solar spectrum, there's invisible light, such as UV and infrared, and there's also visible light that our eyes are sensitive to. So remember, light is a waveform, but it's also a particle called a photon. So for each wavelength, each photon has an energy. And here it can be described by this equation. And the Planck's constant actually links the two concepts together. So what it's saying is the energy of the photon can be found by multiplying the speed of light with the Planck's constant divided by its wavelength. So how does the solar cell work? Well, I always like to use the analogy. Instead of the Goldilocks and the three bears, I like to say solar cell and the three photons. So what happens when you have a photon that has energy lower than the band gap? Well, the photon passes straight through and does nothing. However, when the photon has energy higher than the band gap, then the photon gets absorbed, and the energy is used to excite an electron from the valence band to the conduction band. But in fact, the energy is way higher than what is needed, and therefore produces thermalization losses. So like Goldilocks, it's always good to have photons with energy very close to the band gap of the semiconductor, so that the energy is used efficiently to excite an electron without any wastage. Now, the incumbent technology, so what you have, solar cells in the solar panels on your roof are made of silicon, and they have a band gap of 1.1 EV. That means they're very good at absorbing sunlight near the infrared all the way up to UV. So infrared is around 1,100 nanometers. So for photons that have energy higher than that, for example, in the UV regions, silicon will still absorb them. But as I've said, there will be thermalization loss. And therefore, the practical efficiency limit of silicon is around 29%. So I want you to remember that if photons have energy that is way higher than the band gap, you get thermalization loss. Okay, well, let's just quickly go through how solar modules are made. Well, they actually came from quartzite, which is basically silicon dioxide. So quartzite is mixed with sort of sand. A purified sand is mixed with charcoal or coal or coke, melted at 2000 degrees in an electric arc furnace. You will get 98.5% pure silicon. And then the powder metallurgical grade silicon is then reacted with anhydrous hydrochloride to form what we call the trichlorosilane. And the trichlorosilane, after a few distillations, we purify the halides, and it's reacted with hydrogen, at 1,100 degrees for 200 to 300 hours, which is around 1 week, to produce very pure form of silicon, which is 99.9999% pure. And it means you have 1 impurity atom per 10 billion silicon atoms. After that, we still have to make single crystalline silicon. So we melt the polysilicon and we dip a seed crystal into the molten silicon, which is gently pulled up so that the melt will solidify the seed crystal and adopts the crystal orientation of the seed. And we have an ingot, and then we slice the ingot into wafers, which is then textured to deliberately produce that velvet finish, so you don't get a mirror finish that reflects light too much. And you also have to dope the wafers with phosphorus or boron to form that PN junction, which is the the basic building blocks for optoelectronic devices. And the PN junction is important to separate electrons and holes to the respective polarity electrodes. And then the wafers receive surface coating to pacify the defects and for anti-reflection. And the metal is deposited. So you see these white lines, they're actually metal deposited on the surface to conduct the electrons out for power generation. And then they are sandwiched between glass or backsheet and forms a rigid panel. Now they're dirt cheap to make now, but they still require people to install the panels and the wiring and hook them up to inverters. So there's always incentive to increase the performance further, given the practical limit is only 30%. So how do we do it? Well, we can actually stack a higher bandgap cell onto a silicon cell, and the higher bandgap cell will do a much better job absorbing high energy photons without any thermalization loss, if you remember. So in fact, if you have 2 junction tandem cell, we call this tandem because the 2 cells are working in tandem, the efficiency limit increases to 45%. And if you increase the number of junctions, you can increase the number of stacks, you increase the efficiency further. So it jumps by almost 10% up to 3 junction. However, if you stack more cells, so on the right-hand side, you can see the graph. It shows the ideal bandgap. So you only need to look at the peak. The ideal bandgap for a 2-stack, 3-stack, 4-stack, 5-stack, and 6-stack tandem. You can see that for 5 and 6-stack tandem, the efficiency hovers around 60%, and therefore there's not much incentive to make too many junctions in a tandem. So what materials are suitable for tandem? Well, this graph shows, all the solar cell technologies that people have been working in the entire world throughout the years, and they show you the best cell efficiencies produced in the lab. So now you can see the blue curves represent the silicon cell technology, and you can see that it took around 40 years for efficiency to double. There also other curves showing other types of solar cell technologies. For example, the purple ones represent the compound semiconductors made of group 3,5 materials in the periodic table, such as gallium arsenide. They also adopt the concept of multi-junction, and therefore they have very high efficiency. They're very good for space applications. For example, they're on the International Space Station and on satellites, but they're incredibly expensive to make. They cost around $13,000 to $30,000 per square meter, while silicon only costs around $100 per square meter to manufacture. So you can see that silicon has been going up, steadily over the years. But if you look at the graph carefully, there's this new technology called the perovskites, which only took 10 years for the efficiency to double. So what is perovskite? Well, the form of metal halide perovskites can be represented by this crystal structure and can be represented by chemical formula AbH3. So the inorganic version, cesium lead iodide perovskite, has been discovered around 100 years ago, but no one thought of using it. So for the A side, it can be a cesium or a organic material, which can be methyl ammonium or formiddinium. represented by this formula. The B site can be taken up by metal, which can be lead or tin, and then the X site is taken up by halide, which can be chlorine, bromine, or iodine, or even a mix. You can even mix them. It's got very good optical absorption coefficient, and therefore it can be made in thin film form. Also, you can see that by just changing the composition, you can change the band gap. So why it is so good for tandem solar cells. You can actually stack a perovskite cell on top of another perovskite cell. Okay, so another quiz for you. As I said, perovskite cell can be made very thin because it absorbs sunlight really well. So in the order of thickness, which one is true? Is silicon solar cell thicker than a piece of human hair and thicker than a perovskite cell, or B, human hair is the thickest, followed by silicon cell and perovskite cell, or C, silicon cell is thicker than perovskite cell and then thicker than a piece of human hair? So A, thumbs up, please. Anybody thinks is A? 6, I've got 6, 7, 6, offering around there. B, is human hair thicker than silicon cell? Lots of responses. Wow. Or C, silicon cell is thicker than a perovskite cell and it's thicker than human hair. Okay, well, the answer is A. Silicon cell is around 200 microns thick, which is thicker than a piece of hair. So you can hold it, you can carry it. And hair, depending on, your gene, it can be very thin, fine, or it can be thick. And mine's sort of at the 181 microns range. And perovskite cell, the perovskite absorber cell was actually only 500 to 800 nanometers, plus all the other layers, the whole transport layer, electron layer, and the electrode is around 1 micron thick. So there you go. Now, if you remember, I stepped you through on how to manufacture silicon cell. Perovskite cell is very easy to make. So in the lab, it used to take me 4 weeks to make. And now in the lab, it takes students maximum 2 days to make. Of course, in a manufacturing setting, silicon cell takes much shorter time to manufacture. But imagine if the steps are a lot simpler for perovskite, how easy it will be in the manufacturing setting. So if you remember, it also silicon cell has to go through hours and hours of high temperature process for purification and then crystal growth and slicing. With perovskites, on the other hand, it can be done using solution process. So simply by mixing the organic halide salt with metal halide salt, put it in a solvent and you can deposit on the substrate. So the first video shows how you can make methyl ammonium lead iodide thin film by spin coating that precursor solution on the substrate. And you can see the instant change of color, meaning nucleation is already happening. And if you give it a heat treatment at 100 degrees Celsius, it will form a nice crystalline film. So tomorrow when we do the lab tour, you'll be able to see that happening in the lab. The second video shows one of my students making a cesium lead iodide bromide film by spraying the precursor solution onto a substrate, which is sitting on a hot plate at 200 degrees Celsius. And you can also see the instant change to orange, and that's because the film has a band gap of 2 eV, which corresponds to the orange color. Now, in our lab, we just about try every deposition method we can get our hands on. So you can fabricate perovskite film by spraying, or evaporation, meaning you heat the perovskite precursor without any use of solvent, such that the material will evaporate and condense on the cold substrate. You can evaporate in vacuum here, or you can evaporate in ambient. So the difference is if you evaporate in vacuum, you can bring the melting point down for the precursors. And you can even use a nitrogen gun just to blow the solution, and it induces nucleation straight away. Now, in terms of cell design, it is also very versatile. So we deposit the material onto a piece of glass, which makes a flat panel, a rigid panel, or we can deposit the material onto a flexible substrate, which allows us to make flexible panel. Now, all cells will have something very similar with the substrate, or we call it superstrate because light going through the substrate. So we'll turn it upside down. And we can even swap the position of the electron and transport layer. And we can also use different types of material for electrodes. And therefore, it opens up new application opportunities where flexibility and weight are paramount that the current silicon technology cannot address. For example, silicon cells cannot be made transparent, but perovskite cell you can, because you can thin the material down. You can also tune the band gap so that it's invisible to a human eye, but is actually useful for generating electricity. Silicon cell has a fixed band gap. Therefore, you can only use it as one of the cell for tandem, whereas perovskite, you can use different composition perovskite to make a tandem. A silicon cell is brittle, whereas perovskite cell is not. Now, thin silicon is possible, but the manufacturing cost will go up dramatically because of the complexity of handling. Now, perovskite cells have much higher power to weight ratio, even compared to the gallium arsenide cells used in space. And therefore, they can be considered for maybe vehicle integrated application or space application. Now, in our lab, we run a lot of research projects that are all multidisciplinary. So what do we want to achieve? We've got a bunch of physicists, chemists, material scientists, and engineers, and we all want to increase the energy conversion efficiency, as well as the durability of single junction and tandem cells, mostly perovskite for terrestrial, land, and space photovoltaics, as well as building integrated photovoltaics. And also we're looking at directly integrating cells for photovoltaic electrochemical devices for hydrogen generation or solar flow batteries. So there's some, nice physics involved in the designing of tandem cells. So this picture, there's a story behind this. So I was interviewed by the University of Sydney for an article in the Alumni magazine, and the interviewer was just not happy with the quality of the perovskite silicon tandem cell picture drawn by scientists in the journals. So he puts his hand up and says, I'm going to do a much better one. And little did he know that it was actually a lot more complicated than he first thought. And it took us many back and forth to get the basic perovskite silicon tandem cell structure right. And I must say, this is the best perovskite silicon tandem picture I've ever seen. So in designing the cell, it's actually, it takes a lot of thoughts into it. So for example, there are many layers in the tandem cell. That means we need to get the optics right. So when the light is coupled through layers with different refractive index, the light can actually, the reflected light at the interface can actually experience constructive or destructive interference. So that means they're either in phase or out of phase. So for a solar cell, we want the reflected light to interfere destructively, so the reflection is minimum. So we've got a bunch of very clever physics students, and they employ what we call the transfer matrix methods to look at the propagation of light through the different layers and how they interact at different interfaces. So for 1, 2, 3, 4, 5, 6, 7. So there's around 7 interfaces. Imagine all this light being reflected and interfering with each other. So, there's not just one cell design, there can be quite a few of them. And the idea is to look at what the other layers are absorbing, parasitically we call it, because these layers are actually not responsible for electron hole pair generation. They're actually stealing light from the perovskite or from the silicon. So we want to find out how much light is being absorbed. So for example, this gold layer is very absorptive and we don't like it. We also want to look at the total reflection, which is represented by the red. So the smaller the red area, the better. Also, we work with industry partners a lot. So some of our projects are very industry focused, and believe it or not, even within silicon technology, there are different types of silicon solar cells. So the most common one represented by the orange histogram here is the PERC technology invented in UNSW. So when we make perovskite silicon tandem, we want to make absolutely sure that our perovskite cell is compatible with the PERC technology. We're also working with the heterojunction technology that is invented by Sanyo Panasonic in Japan. Also, we want to make sure our cells got the practical cell size. So believe it or not, many lab cells reported in the literature are tiny, tiny cells. So they're less than 1 square centimeter. Some of them are 1 square centimeter, but we want our work to be industry relevant. So we make them into square centimeters, 10 or even more, more than 50 square centimeter, to make sure our process can be translated to the production easily. Also, as I said, our research is multidisciplinary. So we work with people carrying out techno-economic analysis to look at the cost drivers for our perovskite silicon tandem. So whether the materials we're using or the process steps we are developing, are they expensive or they need to be replaced to make the technology more cost effective? So here you can see what this graph is saying is we don't want the extra cost of tandem. We say that again. We want the efficiency gain from putting a perovskite on silicon tandem to be matched by the extra cost of putting the perovskite on the silicon. So what this graph is saying, for example, if the perovskite cell costs an extra $1.50 to make, to form a tandem, then the efficiency of the cell needs to increase from 20% to 25% to break even. Now, this calculation assumes the perovskite cell will last as long as silicon. So this brings us to the holy grail perovskite cells, which is durability. So the earlier lab cells reported 10 years ago, they only lasted for a few days. But over the years, the durability of perovskite cells improved. But silicon has a big advantage, as they're stable. So they offer performance warranty of around 25 years or product warranty of 12.5 years to 15 years. That means if they fail, you should be able to get them replaced. So you can see perovskite's got big shoes to fill. Fortunately, last year we reported the most durable perovskite cell in the journal Science. Now, because we don't have 25 years to sit around to watch the cells degrade or whether they're stable, we decided to put the cells through accelerated tests. That means we cycle them through temperature extremes, for example, -40 to 85 degrees, and we subject them to high temperature, high humidity condition, for example, 85 degrees and 85% relative humidity. And these are industry tests for photovoltaic modules set by the International Electrotechnical Commission. And we found that our cells not only met, but actually exceeded the industry requirements for heat and moisture. And that was a huge deal. So it was reported in the news. And how do we do it? Well, we had two strategies. The first is we need to understand when perovskite cells degrade and how they degrade. So we put the cells literally in little sealed bottles and put them through heat stress. And because perovskite has organic compounds, if you remember, they've got carbon and hydrogen, they can outgas. So we use this technique called gas chromatography mass spectrometry, which is not a new technique, but it's never been used for looking at the stability of perovskites. So GC separates a chemical mixture. As you see, get all these gaseous volatile products coming out, we need to separate them, and mass spectrometry identify the species. So GCMS has been used for developing new drugs, detecting explosives, screening athletes for doping, and even analyzing soil samples from Mars. So after we understand how and when perovskite cells degrade, we develop encapsulation strategies to protect the cells from the environment that causes them to degrade. So we look at the use of low-cost polymer-based material for encapsulating the cell between two pieces of glass. So again, this is an industry familiar technique that is commonly used for double glazing window and some solar panels. We also look at the effectiveness of two techniques, whether you use the polymer to seal the edge of the glass only, which is in this case with a void in between, or we have the polymer covering the entire cell. So these are common techniques used for glazing, double glazing, for example, or laminate glass, where you have a full area laminate laminating the glass. So in case it breaks, it will hold the glass pieces together. Also, we've got to look at how the electric wires come out of the cell and make sure when it comes out, it's not going to let moisture in. So going back to strategy 1, we use GCMS to identify which type of perovskite, which component of the perovskite and therefore which type of perovskite is more stable than the other. For example, we found bromide perovskite is more stable than iodide. And also the cesium, the inorganic perovskite, is more stable than the formamidinium perovskite, and which itself is more stable than methylammonium perovskite. And we, torture them at different temperature and see what happens. And we therefore deduce the chemical reactions or the decomposition chemical reactions. We also use the GCMS to test the different cell designs to see which layer in the cell is outgassing, if they do, and also the different encapsulation materials. For example, we look at 2 types of polymer, a polyolefin one and the polyisobutylene. They're both used in these double glazing technology. And we also look at how whether it is a blanket-based or etch seal-based method, which one works better. So finally, we found that the blanket approach is the best. And what happens is the encapsulation does 2 things, and it's important that it does 2 things. It stops the moisture ingress and it suppresses outgassing. So if there is any void between the cell and the glass, the perovskite can have an opportunity to outgas and therefore drives the decomposition reaction. Whereas if the perovskite cell is fully covered in an airtight encapsulation, then it has no chance of having that decomposition reaction from proceeding. So the cells do really well in 3 IEC tests: the dam heat, thermal cycling, and humidity freeze. Not only they met the requirements, they actually exceeded the requirements. So for dam heat, they've got to survive 1,000 hours of 85 degrees and 85% relative humidity. They actually survive 1,800 hours. And for humidity freeze, they need to survive 10 cycles of humidity freeze. They actually survive 75 cycles of humidity freeze. And this is a very tough test, because we actually need to first torture the cells between thermal cycling from -40 to 85 for 50 cycles. Then we put it through dam heat and freeze them very quickly. So if there's any water crystals, ice crystals forming within the cell, it will crack the cell. And we found that none of that happened. So continuing the work, we're now extending the durability work from single junction perovskite to silicon perovskite tandem. We're funded by the Australian Renewable Agency. We're also looking at triple junction now. So instead of perovskite silicon tandem, we're looking at perovskite silicon tandem. So that provides a lot of work for our researchers. As you can see, the cell structure becomes more complicated. Now, for the building integrated photovoltaics, we're interested in developing solar vacuum glazing, which is a multifunctional product. So it provides thermal insulation, sound barrier, light control, and energy generation. And we developed some heat transfer model to examine the effect of putting the cell either near the outside pane, on the outside pane, or on the inside pane. of a double glazed unit. And we look at it at different scenarios: hot versus cold climate, perovskite versus silicon cell, double glazing with air in between or vacuum in between. So why do we care? And that's because where the cell sits will determine how hot and cold they will be, and affects their performance, and therefore how much power we can get from the solar glazing. Also, in some scenarios, we found that it may be possible to use the warm solar cell to heat the indoor environment. Okay, last but not least, we've got projects that look at using solar to interface directly with the electrochemistry. So we got a project supported by the Australian Research Council that use solar to produce hydrogen, either through water splitting or some other means. So we're very excited because we have found another way of producing hydrogen without the use of water, and we're able to produce a product that is of higher value than oxygen. And we have just submitted a patent notification for the work. So why do we care? That's because when the solar cell interface with the electrochemistry directly, we can actually bypass the use of electric wires. And then another work, which was reported in Nature Materials last year, we interface the solar directly with a redox couple that is a flow battery. And we were able to achieve the highest conversion efficiency for that battery. So that's the end of my talk, and thank you for listening. And I'd like to take the opportunity to thank my team members for doing great research in our group as well. So thank you very much.
Thank you very much, Anita. And you finished, wow, really close to the 2:45, to the 11:45 mark. So that was really nicely done. Listen, I've got a whole bunch of questions that have been flowing through, and they're still coming. So my apologies if we don't get to all of them, all of you out there in Scholarland. I'm gonna do my best to try to sum up some of the questions here. And for those of you who are non-scholars but listening to this and you've sent through a question as well, I'm going to be preferencing the scholars over you. I'm sorry about that. So if we get through all of them, then I'll get to your questions as well. I want to kick off with Anita. Can you talk a little bit about where solar sits in sort of the landscape of the various energy sources? You've made a good case for the fact that it's very efficient and it's very affordable now. So how does it stack up against other energy sources in terms of efficiency and cost and affordability? What are its major competitors, if you like? Should we put it that way?
Yeah. So I think I've shown the cost curve, didn't I?
I think you did, but if we could have a quick look at that.
Share screen, share. Right, so 10 years ago, solar was more expensive than wind, and now they're sort of pretty good. So they are on par. And we can see that onshore wind power is actually cheaper, can be cheaper than solar. Yeah, so I think that instead of seeing them as competitors, we should see them as complementary technology, because you would think that when there's no solar, there's wind, and when it's a nice sunny quiet day like today, you will want the solar panels to be firing and producing electricity.
So it's less about choosing one over the other. It's more about having a whole suite of things that we can choose from,
yes,
that we can put up wherever it's useful to do that in order to get the energy that we need.
Yeah, that's right.
Okay.
So you can see here, a big part of renewable is still hydropower, which I think is great, because not only hydropower is a source of energy, it's actually a source of energy storage. So, you know, when it can be powered by renewables, and, you know, there's potential energy being stored in water. So is hydrogen. So hydrogen itself is a fuel, but you can see it as a carrier. So that's why the Asian countries like Japan and Korea are interested in looking at green hydrogen, and the Australian government is really interested, because we can use solar to produce hydrogen, and we can export our solar energy through hydrogen to our neighbouring countries.
Next question that's come up, and this is a combination of a few different ones here. So I'm going to try to sort of sum some of them up. Again, you've made a pretty solid case, right? I think you've won many of us over in terms of solar, really nice, high efficiency, low cost. It's all good, but there's no getting around the fact that there's a certain amount of energy that goes into and waste that comes from the manufacturing process. So can you talk a little bit about that side of things? I mean, one of the questions that came up was going back to, I think, what is probably a little bit of an outdated notion now, but I can remember you were talking about when Professor Green came and spoke at ISS 2011. I remember hearing around about that time the idea that it takes more energy to make solar cells than you get back in the lifetime of the solar cell. And you hear that still around a lot.
Mm-hmm.
Can you talk about that? Is that still the case? And also, what about the process of manufacturing and the waste and energy that goes into that? How do you factor all of that in, and how does that add up into the efficiency and the cost of solar cells?
Yeah, that's really interesting. And that's something I didn't even know until a few years ago, that we did a life cycle analysis looking at comparing silicon technology and perovskite. Then I realized that making silicon actually takes a lot of energy. But there is a but. So there is quite a lot of, carbon emission involved if you use fossil fuel energy generation to make solar cells, which we still do. But what we've found is, and in fact, making the silicon wafer is actually very energy intensive and is much more intensive than making perovskite cell, which, to my relief. But what we've found is, because over the years, people are learning by doing, and they are getting much better at making, purifying silicon, and they can do it at scales. The life cycle cost has come down dramatically. And usually, most of the time, you'll find that the environmental cost is associated with manufacturing cost. So manufacturing cost is actually quite a good indicator of the environmental impact. So you can see that the manufacturing cost has come down dramatically, and so is the energy used to produce silicon. And we found that I think the payback, just for payback of the energy used to make the silicon panel, actually is only a few months. So it's not big. But it is true. I mean, you've got to mine the materials, and the aluminium frames are, they are heavy, they cost energy, and so is the glass. So people now are talking about recycling. How do we, make best use of the embedded energy in the solar panels?
Yeah, that's another question that came up a couple of times. So what's the ability to take the solar cells at end of life and be able to actually turn them around and make new ones? Is that a relatively simple thing to do, or is that a very difficult thing?
Okay, so interesting thing, two things I want to say. Glass is actually the high cost item. So it costs around $10 per square meter. And if you remember, it costs around $100 per square meter to make a silicon module. And the glass is 1/10 of the cost. So glass is important if we're able to recycle them. They're pretty easy to recycle. The hardest one is actually the laminate. So you remember I talk about encapsulating the cell with the glass, and it's done by laminating the cell onto glass using a material called EVA. So you've got to peel that off, and that is not as easy, but it's doable. And also, are we able to recycle the little metal on the cell? Is it worth it? So people are looking at what is worth it and what is not. But glass definitely is worth recycling, and so is the aluminium frame.
Okay. Now, you talked about a number of different technologies throughout your presentation here today, including the notion of the tandem cells, and layering and bringing in different materials. So one question that came up was, how do you decide which types of materials to use for those tandem cells? And does the order matter? Does it matter which one you put first?
Oh,
so
yes.
That's part A of the question. I'll get to part B in a second.
Yeah. So you always put the high band gap cell closest to the sun. So what happens is the sun strikes your solar cell, the blue light or the UV light gets absorbed first by the top cell, and the top cell won't absorb the green and the red light, the green, yellow, orange, and it will pass through the top cell. And so it will trickle down to the mid band gap cell, which absorbs the green, yellow, and then it will trickle down to the lower band gap, which absorbs the orange and red. So the band gap is always closest to the sun, and then the lowest band gap is always away from the sun, so that you can divvy up the solar spectrum, so to speak, between the cells. Okay, so materials, you've got to choose something that is hopefully low cost. You've got to choose something that you can tune the band gap. And very importantly, you've got to choose something that is high performance. So there are plenty of materials out there. They're probably low cost, earth abundant, non-toxic, but they don't give you the performance required. Now, silicon cell is pretty efficient, right? So it's around 20% commercially or 25% in the lab. You really don't want to put a bad cell on top of the silicon cell, which steals the sunlight from the silicon cell and makes the entire tandem less efficient. So the rule of thumb is if you choose a material, that's got to be at least 20% efficient, and perovskite can do that. So in the last 10 years, the efficiency now is 25.5%, which is pretty amazing. So that's a good material. Gallium arsenide is a good material. But then because it's not solution process, it's very hard to integrate the two materials and make sure the crystalline structures still line up and there are no stresses, there's no thermal stresses, there's no, strains in the crystal structure. So we have, in 2013, we have projects where we look at integrating 3-5 cells onto silicon. But then the cost doesn't stack up, right? So you're putting a $3,000 or $30,000 per square meter cell on top of silicon to improve the efficiency by how much? And is it, economically, does it stack up? So that's why there's so many people interested in stacking perovskite cell and silicon, or even stacking perovskite cells on top of each other. And you can tune the composition in the band gap easily, which cannot be done by other materials.
So that leads to the part B of the question, which is,
sorry.
given that, no, that's okay. Given that you can tune those things and you can get them in the right order, how far can you go? Like, why don't you just keep adding layers until you've got as much efficiency as you could possibly ever want, and you're just trapping it all in? Why can't you just keep going?
Yeah, so if you remember, I showed that that diagram where you can keep going, but the complexities outweighs the advantage. So if you remember, and if I can find it, I can find it. Good. Share screen. Share. There. So you can see that there's lots of incentives of doing 2-junction, 3-junction, or 4-junction. But as you go up to 5-junction and 6-junction, I think the gain outweighs the pain, because every time you introduce an additional cell, well, you think you're introducing extra layer, but it's not. Usually introduces, 6 layers, 4 to 6 layers additional, including the, the absorbent material itself. And the integration is not as easy as you think. Integration is always the toughest thing to do. So I think, 4-junction, pretty much we can stop there.
So it seems like there's a number of the scholars who are thinking about this from very much an engineering and bringing a product to market point of view, because there's been a few questions which are coming at it from a similar point of view. You can come up with all sorts of very clever designs, you can come up with all sorts of clever technologies, but what matters in the end is rolling it out into the world. So can you talk a little bit about that side of things? As someone who's working on some of the most efficient technologies in solar in the world, what's the turnaround time to actually then get it to market? And what's the current state of that in the world? We've got a lot of old school, lower efficiency solar cells out there. How quickly are we going to be nailing these things to our roofs or using them in other applications? Is it a long way off? Is it very close? What's the turnaround time?
So it does depend on the application. So, we can look for the tandem for the classical application, solar farms, rooftops. So the challenge is the durability of perovskite, right? So we want to make absolutely sure it lasts as long as the silicon. And also, if you can see, there's a bit of lead. It's not a lot. We're talking about nanometers of lead, which is 10 times less than the lead used in the solder. You solder the silicon cells together. It's actually 10 times less than what is used in silicon. So the perception, we've got to overcome that. And if we use those materials, we're going to make sure they don't leak out. Even though they're there, there's no chance of them leaking out. So that's the challenge for the classical, use. The other one is the more niche application. So BIPV, building integrated photovoltaics, that the challenge is integration, but also just complying with all the different standards, right? So when you have a multifunctional products, that means you have, multiple types of standards that you to comply with. So it's not just a solar module anymore. It's actually glass that got to comply with whatever standards that apply to glass. It doesn't break, doesn't hurt people. And also needs to comply with electrical standards because it's actually an electrical, component that you've got to comply with that. And then you've got to comply with the building code and the construction code. So these are the sort of, for those niche application. And if you integrate cells onto vehicles, onto the bonnet, then a whole lot of other crash tests and shock tests that it has to comply with. For space, there may be an opportunity as well because the cost is so much cheaper. We're looking at perhaps $10 to $100 per square meter, as opposed to 30,000 per square meter. And there are lots of, Starlink satellites, they're going out, 42,000 of them in the next 10 years. And there's commercial space market that maybe low cost solar is interesting. Then we go for the performance because we don't want to spend all that money, even though it's still cheap. We don't want to spend all that money sending solar cells to space and then they don't work as efficiently. The good thing about space is there's no moisture. So perovskite is sensitive to moisture and it's it's a vacuum, but we do need to protect them from outgassing. And also satellites do not have the same lifetime requirements. They don't usually last for 25 years for commercial satellites, maybe 2 to 3 years. So there is a market for that. And our students in our school of physics are actually very excited about the prospect of sending ourselves to space in the next 2 years.
Anita, we could talk about this and I could ask questions from the scholars that's still coming through. There's so many really good questions that have come through here, but we are going to have to bring it to an end. So thank you to everyone who did submit a question. I'm really sorry if I didn't manage to get to it or paraphrase it in conjunction with a few others. But I'm really, really impressed by the questions that have come through. It is traditional at the ISS for one of our scholars to deliver a few words of thanks. And even though we are online, we're still going to do that. So I would like to hand over to one of our scholars from Red Group. Olivia Seeley has stuck up a hand and said, I would really like to give the first thank you. So we're going to ask Olivia to turn on her camera and her microphone and we'll spotlight her to give a thank you. Over to you, Olivia.
Hi, just on behalf of all the ISS scholars, I'd like to extend my gratitude for the time you've given us. The insights you've provided into the next generation solar cells were truly fascinating. And I know that personally, it was really insightful learning about how such advancements have the possibility to make huge changes. So thank you.
No worries.
Thank you very much, Olivia. And that's it. We are underway. That's the first lecture of ISS Online. So thank you all for turning up, both scholars and our wonderful other guests joining us from the Physics Foundation, friends and family.